Hi. So the first thing to note is that my talk is on Flash, and we'll also note that I work at Seagate, which is a disk drive company, and so you'll think, why is a guy from a disk drive company talking about Flash? Well, so last year, Seagate acquired Avago LSI's Flash division. We sell a full range of Flash devices, from SSDs to embedded cards and all sorts of controllers, all sorts of good Flash stuff. So I have nothing against Flash. I'm encouraged to use Flash, in fact. But this presentation really is on where does Flash actually make sense. I also have a personal agenda, which is I hate burst buffer. I hate the word burst buffer. Everyone uses the word burst buffer instead of saying Flash. If you mean Flash, say Flash. Don't say burst buffer. It drives me nuts. So I'm going to explain what a burst buffer is and what it is not. And I'm going to explain where it makes sense to actually use Flash. Where I think it makes sense to actually use Flash. You're actually welcome to disagree. All right. So why do you want to use Flash? Well, it clearly has a lot of advantages over hard drives. It is much faster latency throughput, much faster for seeks. It's great for random I/O. On the other hand, it has some negatives as well. It is more expensive. It is debatably less dense, although flash densities are going up. And it has limited write cycles, so that's an important factor at the moment. Again, everything will change in the future, as everything does. But at the moment, if these things were not true, would we put Flash everywhere? Of course, right? If it's not expensive, if it has as many write cycles as disk drives, if it's as dense, and it has these other advantages, of course, let's use it everywhere. It doesn't, so let's look at in a little more detail as to where we can make trade-offs. Performance, obviously, cost, durability, and one that kind of gets left off the list a lot is system complexity. So if you have something like quote-unquote a burst buffer, that means that there's additional software that gets involved in the system. Okay, so where can we use Flash? So Flash in particular with respect to Lustre, which is our large-scale systems that we're talking about. We can put it on the MDT. We can put it on the OSS servers, and that's different than putting it on OST devices. And then you can also kind of do something completely different, which is like putting Flash in front of Lustre, kind of outside of Lustre. So on the MDTs, so generally assumed by a lot of our customers, in fact, some of our customers, in fact, to think that the MDT is a perfect candidate for Flash. It's got a lot of small random I/O. You want to do a lot of high IOPS. It sounds like a perfect place to stick Flash devices. Which is true if you have a very small MDS. If you're comparing a single spinning drive to a single SSD, absolutely those things are true. But if you're talking about a large-scale system, right, where you have a lot of storage, you have a lot of particularly a lot of spinning spindles in your MDS devices, you can get a lot of IOPS out of a lot of spindles that spin at the same time. So if you take a 7+7 RAID 10 of 10K RPM drives, right, you can get as many IOPS out of that as you can with SSDs. We did the testing. We cannot get any improvement on the I/O rates through the MDS, replacing those spinning drives with SSDs. So we're not going to put SSDs in the system because it's more expensive. They have fewer failure rates, and they're not don't have as much capacity. So it really shows no improvement. So you have to, and this is all dependent on scale, right? As I said, if you have a scale of one drive, it's going to make a huge difference. But at some point, you're going to reach the limit of the I/O operations that you can do through the MDS itself. I just realized I'm speaking really fast and to an audience full of people that may not have English as their first language. I'll try to slow down. Sorry. Okay, so because you can have a lot of IOPS with a RAID 10 7+7 hard drives, we don't put, for instance, SSDs, even for RAID 10 bitmaps or journals on the MDS. The disks are less expensive, they have much better durability. Despite all this stuff, sometimes have trouble convincing customers that we shouldn't put SSDs, and they want SSDs anyhow. So if they demand it, we give it to them, but it's not an ideal use case. So there's my nice conclusion in blue. It makes sense for small MDTs, but it does not generally make sense for large MDTs, especially when you realize that the MDT itself, the MDS and the MDT, have their own limitations. And if you can reach the IOPS limitation of the MDT itself, the software, having faster hard drives in the background doesn't help. So flash on OSTs. There's a bunch of different ways you can put flash on OSTs as well. And I'll talk about 4 of them, I guess. So SSHD is the first one. That's a hybrid drive. They basically are hard drives with a bunch of flash at the beginning, and they're used basically transparently as a block device. You can also use flash just for your local OST metadata. So this is not Lustre metadata. This is file system metadata for your local LDiskFS file system. You can create an entire flash pool of all flash OSTs, and you can create a flash cache on the OSSs. So this is not in front of the OSSs, but on the OSS itself. You can put flash as a kind of a tier below LDiskFS or in your MD RAID layer or something like that, your RAID layer or something like that. So SSHDs, solid state hybrid drives. So they're basically magnetic media, so they spin with the same characteristics of hard drives. They have the same overall sustainable I/O rates. Generally, they have DRAM in them where all the small I/Os are stored. And in case of power loss, you take these, you take the DRAM and you back it up to flash using the back EMF of the spinning platter. So you lose power, the spinning platters have some momentum, you pull the energy out of that through the motor, you basically have a battery backup kind of through the spinning platters, and you write the DRAM to flash and save your data that way. So that's for anything that happens to be in DRAM, which is basically so you get a very high DRAM rate caching in these hybrid drives. And then normally, so that's one use of the flash, and then the other use of the flash in the hybrid drives is that it's used for read caching. So there's algorithms inside the drive itself that pull or keep particular items that are high request rate items. It pulls them into flash and then serves them from flash. So how is this better, worse, different than anything else for OSTs? So the streaming performance is the same as hard drives. But on the other hand, streaming performance for hard drives is actually pretty good. It's the random I/O for hard drives that is not so great. So the streaming performance is the same, so that's acceptable, kind of neutral. There are also, in Lustre, there are other caching layers. So the client caches stuff, OSTs can cache stuff. So that potentially limits the usefulness of the read cache. But on the other hand, the write cache is actually quite helpful for a number of reasons. So first is your random I/O rates now can go way up since you're actually really writing to RAM rather than a spinning disk when you're doing these small I/Os. We generally report about double the random I/O rates to the drive. You also can remove the effect of the local file system metadata updates. Again, even if you're doing large 1 megabyte I/Os to Lustre, that does not translate to large 1 megabyte I/Os to the drives themselves. The drives themselves see all of the local metadata updates for the LDiskFS file systems. So bitmap changes, journaling, all that stuff. So you can you can get rid of those interjectory IOs that show up in the IO stream to the drive. You can get rid of the effects of those by having hybrid drives. And then potentially you can also do host pinning, where your host actually tells the hybrid drive that it wants to keep particular things in that flash layer. That is more involved, but it's a potential savings again. So you don't have to buy dedicated hybrid drives, dedicated SSDs to do this. You can put them on your larger, more stable drives. Oh, and the other thing about this is that anything that is in the flash layer is always backed up to the spinning disk, so that eliminates some of the write limit problems and resiliency problems of the flash itself. So you're guaranteed basically that anything you write to this drive, it may be in flash, but it's always going to be on the disk as well. Okay, what else can you do on OSTs? You can dedicate actual SSDs for the metadata operations that you know you're going to operate on the OSTs. Again, not Lustre metadata, but local file system metadata. So block bitmaps in ext4 lscfs, write intent bitmaps if you have MD-RAID kind of layer in there, which make a really good place to put, it may be a good performance improvements to put those on SSDs. For those of you that don't know, MD-RAID has what's called a write intent bitmap. So it writes down ahead of the actual writes to devices where it's going to write data, so that it can ensure that in case something goes wrong, you lose power or whatever, when it rebuilds, it focuses only on those ones that it knows that it was writing. So it can check those ones. It basically is a speed optimization during rebuild. So it's helpful to put those on SSDs because you write them a lot. You write them at every write. You overwrite them as well, and they also are not critical. So if you lose the SSD that happens to host this, all that means is that your rebuild is slower than it might have been, but it's not as critical. It's not going to destroy your file system. It just means your rebuild is going to take longer. External journals. So the issue with putting external journals on SSDs is that they're writing constantly, right? And as I said before, Flash has limited write cycles. The other thing about journals is that they're sequential, which hard drives like. So this one's debatable, but you can argue that if you use a fast hard drive, it's more reliable and it's a good use case for hard drives, and therefore it may make more sense to use a high-speed hard drive than an SSD for journals, for external journals. All right, Flash OST pool. So in Lustre, there's a ability to group particular OSTs into a pool, and you can have users specify those OSTs via LFS set stripe. So LFS set stripe -- pool equals X. So you can actually set up a set of OSTs that are full of SSDs if you want to. So in one sense, this is great because now you have dedicated, really high-speed I/O for anything that you send to that pool. It's great. So if you have if you know you have a load that's going to be random I/O intensive, put it on the SSD pool, and you can read and write to your heart's content. So that's great. It's also, in a sense, if you use a pool, it's easy to change the size of the pool. Well, easy, quote unquote, in that you can add more SSDs and add more OSTs to your system. So if you're comfortable adding OSTs to your system, you can add some SSD OSTs to your system, and kind of change your ratios that way. Whereas if you have fixed ratio systems, like you have a a hyperdrive, for instance, that has a fixed ratio of flash to a spinning disk. You can't do that. So the kind of the neutral part of this, or maybe the negative part about this, is that you have to now specify ahead of time where your data is going to live, right? If you say that you're going to use this flash pool, you have to tell Lustre you're going to use the flash pool, otherwise it will just use random select, well, its own internal random selection policy. So, so this puts a lot of burden on the actual users who are now using the system, right? So that they have to make the decision that this data has to live on the flash and this data has to live on the spinning disk. So it's not automatic. So that's the penalty you pay. Another positive actually here is that it's actually quite simple, right? It's simple to do. Anyone can just set this up, and it doesn't require any new sets of software or any new testing or any new HA or anything like that. Okay. Another way you can use Flash on OSTs, or OSSs, I guess, is to put kind of a new layer of Flash in between a standard set of disks and the LSFS block layer. So you can call this a Flash cache. People have called it a small block accelerator. There's different ways you can name it, but the basic idea is that.
Is it burst buffer?
No, this is not a burst buffer. We'll get to the burst buffer. This is not it. No. So no. Don't get me started. Don't get me started. All right. So yeah, the idea is that in this case, all IOs flow through a local flash cache, right? A local cache device, and may or may not subsequently be coalesced down to spinning disk. So in this case, the local flash cache is responsible for keeping track of what data is locally stored in the flash and what data has been migrated off to spinning disk. So this has a lot of good positives as well. So for one, if you have random writes, you can kind of coalesce them into larger writes that your flash tier then kind of moves down to the spinning disk. Doesn't help with random reads though. Random reads, well, if they're not cached already, the random reads would still have to go out to the disk. It can cache reads, of course. Now you're subject to the cache read policy of your flash layer there, but there's no real penalty for flash miss in that it just sends the request down to the actual spinning drive and gets it back as fast as the spinning drive can. So not everything is on SSDs, but nothing ever will. No system anyone's proposed, except for maybe Intel, I don't know, would say that everything should be on SSDs. So the other thing is you can take now the same flash cache and actually put it in front of a bunch of different individual OSTs. So you can kind of increase the capacity of this and use it as a more global, at least an OSS global cache rather than an individual OST local cache, which would be so you can get a little bit more optimization. If you have, if you tend to use one OST more, more of your flash can be dedicated to that OST. Another advantage is it's transparent to the upper layers. You don't have to tell, you don't have to make a decision that this is LFS, that stripe needs to go to this pool. Everything that's used random IO would effectively go through this. As I said, you kind of now depend on the cache policy that you have in there, but potentially you can adjust that to your particular use case too if you want to. So I think in general this is a good solution for utilizing flash in large-scale Lustre systems. All right, here we are, interposing flash layer in front of Lustre, a burst buffer. So here's what a burst buffer is. All IOs are written to the burst buffer set of software, which sits in front of Lustre. That layer of software sends, based on its decision, sends IO to local flash or to the secondary storage system, which would be Lustre. So it sits in front of Lustre, it's not behind Lustre. So that's the difference of burst buffer from any of these others that I've talked about. And the basic idea of a burst buffer is that you're doing defensive I/O. You're storing a burst of basically a memory checkpoint into flash quickly, and then draining that flash slowly off to storage system. That's the original definition of burst buffer, and it has definitely become conflated with all sorts of other meanings since then. But that's what I think of when I hear burst buffer. So, all right. So there's two layers in this system. There's a flash layer handled by flash software, and then there's the disk layer handled by Lustre. So there's potentially advantages here, and we'll get to that. I have more detail on this later, but right now I'm just trying to describe what it is. So there's more complexity here. There's potentially an additional read latency if you actually read back through that flash layer again. That's, again, you can avoid that, but it may make your software more complicated. There's a new set of software. There's also new front-end semantics, potentially. This is not necessarily a POSIX-style API anymore, although you might do that through something like PLFS. It does accelerate all your I/O, your random and sequential I/O, because you're sending it all to high-speed flash. And there's no Lustre overhead for doing this, right? So you're kind of not talking to Lustre at this point. Another advantage is you can actually make a more simplified backend interface, right? So if you have a layer in front of Lustre, now you don't need full POSIX all the way to the backend Lustre. You can reduce that interface to, you don't have to worry about renames and things like that. So a restricted interface is actually potentially useful and potentially helpful for removing some of the load on Lustre. So those were some possible ways of architecting flash into your systems. Then the question is, well, when should we actually use flash? So here's some use cases. Defensive I/O is the burst buffer case, so that's the first one I'll talk about. 2BB or not 2BB, right? Okay, so the graph over there is kind of the red is the capacity utilization of your flash layer, and then the green is the capacity used of your disk layer. So the idea is you fill flash really quickly, you slowly drain that off to disk, right? Then you fill flash really quickly and slowly drain out off to disk as you're doing these checkpoint stores, right? So you can see the interesting thing about this graph is not the flash layer, but the disk layer. So the disk just keeps going up, right? You're filling it more and more and more and more. So the implication clearly is that you need a large capacity disk storage system in order to make this thing make any sense, right? So the ratio of storage in your flash layer to your disk layer has to be relatively small. So you have to have a lot more disk than flash. All right, so, and we will see that if you have a lot more disk than flash, that mitigates the whole point of flash in a lot of ways. All right, so the canonical use case for burst buffers, you have a petabyte of RAM that you're trying to store to flash in 5 minutes. And then you take that petabyte of RAM that you've now stored in flash, drain it off to disk in the remainder of your hour. So in 55 minutes, you drain that off to disk. So I'll choose some hard drives you can buy today. You can buy a 500 megabyte a second SSD at a terabyte, versus a 100 megabyte spinning hard drive at 8 terabytes. You're welcome to do your own math. I encourage you to do your own math. I'm not trying to say that these are the numbers, but they're representative. Okay, so with those numbers, to get a petabyte to flash in 5 minutes, you need 3.3 terabytes a second, giving you a number of 6,600 SSDs you need to do this. To drain that now to the disk, in over 55 minutes, you only need 300 gigabytes a second to do that, which means you only need 3,000 hard drives. So look at those numbers, 6,600 SSDs versus 3,000 hard drives. Well, you're paying for a lot of SSDs there. You're getting it, you're doing it all in 5 minutes, but there's some, that's a large number of SSDs. All right, now what we said before is your backing capacity needs to be a lot bigger. So we had a petabyte of storage in our flash layer. Let's say we have 50 petabytes, so we can store 50 snapshots of our memory in the disk system. So to do that at 8 terabytes requires 6,000 hard drives, right? Well, so because we have this big capacity requirement, right, we effectively we have more hard drives than we need for that performance. So actually our performance is better than the actual requirement. So we can actually store that whole petabyte of data now in only 27 minutes, right? Because we have a lot more hard drives because of our capacity requirements. All right, but we already paid for 6,600 more SSDs in this system. Well, let's, instead of buying SSDs, let's just buy hard drives instead. And let's call it a 1-for-1 cost ratio, right? We know it's not actually. Solid-state drives are more expensive, so you could actually buy more than this. But let's say it's 1-to-1. Now we have a total of 12,900 hard drives in our system, and now we're down to only 12.9 minutes, right? So we can do the burst buffer thing and do 5 minutes to flash and 55 minutes to disk. Or we can skip the whole burst buffer thing and do the whole thing in hard drives in only 12.9 minutes. Well, so that's something. That's you're saving 7.9 minutes. But it's not 55 versus 5. It's 5 versus 12.9. So what we get there is, for the cost of this delta, right, of the flash over the hard drive, you save 8 minutes, and you lose a bunch of capacity as well, because we know that our hard drives are much bigger capacity than our SSDs. So we actually have a lot more capacity since we traded in our SSDs for hard drives. So our capacity now is actually 103 petabytes. So we get an extra 53 petabytes. We lose 8 minutes, right? So that's a trade-off worth thinking about. Oh boy, I'm gonna have to speed way up. This is the one I wanted to talk about anyhow, so I'll talk about it. So the point is that yes, this burst buffer can save you a little bit of compute time, can save you some time, but there's a cost, right? And there's a trade-off. It's not a given. So do the math. All right, job-based staging. So this is a different use case. You can use your Lustre flash pool, the LFS one, or a burst buffer potentially. So job-based staging basically means you move the data into the flash ahead of the job. You move the results of the system, results of the computation out of the flash to the disk after. So so the big problem here is that you kind of have to copy the data twice. So if you don't double buffer that, then that means you have to wait for that whole ingest time and then wait for the whole outgest time. So you kind of have to double buffer it. So you have to have two sets of flash that you're kind of alternating. And it also requires you to know which files you're going to be working on for each job, so you can know what to pre-stage or not. So this can make sense if your job is amenable to this kind of operation. So if you know what needs to be used and doesn't need to be used, and you're comfortable, doing that pre-staging movement ahead of time, that's great. And as I kind of was pointing out last time, depending on the relative sizes of these things, it may not make sense to put it all in a smaller flash tier rather than a larger disk tier, because your larger disk tier kind of gives you the performance because it's big. All right, random I/O. We kind of already talked about this a little when I was mentioning hybrid drives, or the OSS flash caching ahead of time. So in general, it's good to add flash for these kind of use cases. So if your jobs are lots of random I/Os all the time, yeah, you're probably going to want more flash in your system in some manner. The flash pool is great if you're willing to take that manual direction step, so you are deciding what needs to go where. And then the burst buffer, if you are if those extra minutes of compute time matter to you, then they matter to you. All right. Streaming I/O, not so important to have a lot of flash. Kind of obvious. There's some advantages if you use a flash pool. You can still get higher I/O rates to a flash device than you can for a spinning disk. So as long as you can appropriately maneuver that data to the right kind of long-term storage location, then that makes sense. Capability duty cycle. So I stole this graph from our friends at DDN. This is from a presentation that they made. Their presentation stated that 99% of the time the storage bandwidth utilization of their system was less than 33% of their maximum, and that 70% of the time it was less than 5% of maximum. They were doing a study to look at their flash system. So this is what their graph looked like. So I redrew that, putting all of the overages at the end, right? So the 99% basically is that big spike at the end. So that's 100% is the speed of the flash system, 20% is the speed of the drives. I'm using my same 500 versus 100 megabytes a second. So the green line is the capability of the disk system, and the red system is the flash system. But you can see that the utilization is relatively minor. If you move all of that extra capability and just don't use the flash and let it fall over to the capacity side, you're going to cost a little bit of time, right? So it takes you a little bit of extra time now to do that, but it's not much. It's only about a 5% of an impact there. So again, for the extra cost and complexity of putting a SSD system in front of the hard drive system, there's a little bit of a gain, but it may not be worth it. Where am I at, Orlando? Is time up? All right. So this is kind of my summary. In various, again, you're going to have to think about it yourselves, of course, but different manners of doing things. I'll let you look at this afterward, but basically I'm going over what I was just saying. And my conclusion, like I said, for the burst buffer is it really depends on whether those extra few minutes are important to you. It depends a lot also on your choice of assumptions of how exactly, how much faster and how much capacity these different storage layers have. So what do we do with flash? What does Seagate do with flash in particular? So, as I said before, we make flash devices and we sell flash devices. All of the systems that we Seagate Systems Group sell contain flash in some form. I like to think that we use flash where appropriate, where it makes sense. Another point I think that is important to stress is that both flash and hard drives are getting faster and bigger. So faster and bigger, not just bigger. So again, it changes the dynamics and those calculations that we were looking at before. If hard drives are getting faster and you have a lot of them, it makes more of a difference than if fewer SSDs are getting faster. On the MDS, we have fast RAID 10, no SSDs. On the OSTs, we do use SSDs for a particular LDISC improvements. And we're going to shortly be offering a OSS flash cache, as I was talking about before. I think that makes sense in a lot of ways. As for the burst buffer, the interposing layer in front of Lustre, as I said, think about it, do the math. Don't just hear the word burst buffer and think that you need one. That's it.
Christian.
When you're talking about OSS flash cache, are you thinking about a hardware implementation or a software one?
Ultimately, all hardware implementations are software, right?
Right.
So So in this case, you're kind of talking about a dedicated firmware-based unit versus special, flash software. When you say I'm talking in general cases here. Are you asking about Seagate specific plans?
Well, both.
Okay, so the general case is it doesn't matter either one.
In general case, it doesn't matter.
Yeah. And in Seagate specific case, we'll find out at supercomputing.
We'll see. Okay, thank you. No answer, but good answer.
So I don't really have a question, but I do have a couple comments on burst buffer, just for your consideration or maybe other people's consideration. So a lot of the customers that are talking about burst buffer and desiring a burst buffer, their applications are synchronous, right? So they wait for the write to complete, and so your compute nodes are idle. So you really have to factor in that cost to the whole burst buffer thing. Mm-hmm. Also, this is maybe tangential to your talk, but you've neglected to talk about what you can do while your data is in Flash. You can, you have your data in a single place. You can change the format. You can change how it's stored, which is important, again, to some of these customers.
So yeah, if you know that your data is in a high-speed medium, you might choose to do more manipulation of that data, absolutely. As for the time impact, yes, if your applications are stuck doing I/O, waiting for those drives to store your data, when they could have come back sooner had they, had you stored to a faster storage media. Absolutely, that's a real cost in your system. My point is that looking at the math, you have to decide how much that cost is worth to you. That's all. So there's, in my example, there was a few minutes of savings. If that few minutes of savings, and on large-scale compute systems, the few minutes is worth a lot. Absolutely. I'm just saying, don't make an assumption. Look at the math yourself for your system, and do that math. Do the calculation. All right.
Thank you, Nathan.